Thank you so much to the organizers for this workshop, and thank you for being here to listen to my talk. I'm going to talk about moving habitat models and taking a numerical approach. What's going on? There we go. So moving habitat models are motivated by climate-induced range shifts. So what we're looking at here is the lobster population being more abundant in this northern region compared to the southern region over these years, 1967 and 2014. So lobsters require a certain water temperature to go through different life stages. For example, actually reaching maturity and being able to reproduce and contribute to future populations. So what's happening here is as the water becomes too warm in these more southern regions, the populations that actually contribute to future or the individuals that actually contribute to future population levels are the ones that are more northern. And so what we end up seeing is this range shift correlated to a climatic niche. And we want to ask what mechanisms actually support these successful range shifts as well, like asymptotically, can they do this for all time? And then as well, we're interested in transient times, what kind of, what indicates maybe a high risk population in terms, if we're thinking in terms of conservation. So for the moving habitat model framework that we work with, it's a reaction diffusion equation. We idealize space to one dimension, and we structure space with a suitable habitat and unsuitable habitat. And we do this by introducing these two interface points where we have x equal to L1, x equal to L2 moving in space. And that's those temperature isoclines, for example, that are moving in space due to climate change. And so these bound the suitable habitat where density changes because of dispersal and logistic growth. And then outside the suitable habitat, we have density changing due to dispersal and mortality. So you can see across my habitat types, I have differing dispersal rates. So we can motivate this with the songbird here, this yellow, thanks to the yellow breasted chickadee. And these birds prefer wooded areas where they can be protected. And if they fly across, for example, path, right, they're not lingering there. They fly quickly across, but they maybe sit and relax in their wooded area where they have protection. So that would be an example of this habitat dependent dispersal rates. As well, we can, across our interfaces, we have to introduce coupling equations. So we have coupling equations for flux and density you can see here has a jump given by these proportionality constants K alpha and K beta. So K alpha and K beta are dependent on the diffusion rates and as well on habitat preference. So we explain the habitat preference via a probability that an individual moves into the suitable habitat when at the trailing or leading edge. And we can motivate this with an example of the Fender's blue butterfly, which will actually bias its movement towards its suitable habitat if near a habitat edge. So when L1 and L2 are moving at the exact same constant speed, we can obtain a lot of analytical results. However, for general L1 and L2, we want to we have to use numerical methods. So our numerical approach has to somehow deal with these moving interfaces. We have these 2 points of prescribed velocity, and we're actually going to exploit these because we know exactly where these points are. And they're explicitly described in the equation. And so we use this Lagrangian approach where we take a mapping of our xt coordinate system and we map it to a new coordinate system, which we call the yt coordinate system, where L1 and L2 are now fixed in space. And so this is an example mapping here that you can see, and this is the mapping that we use today. And this mapping fixes our interfaces at 0 and L. We have to restate our system over this new coordinate system. So we call this the reference frame. When we do this, we end up with an advection term, and this advective term is dependent, its coefficient is dependent on y, so on space and time. And as well, we introduce time-dependent diffusion coefficients. Okay. I also want to note that because we're working on this infinite domain, we do need conditions at infinity. So what we assume is that u approaches 0 as y approaches positive or negative infinity. And this is really reasonable because If the individuals are really far away from the suitable habitat, then we shouldn't find them. Well, very far away from the suitable habitat, we shouldn't find this species there anymore. So we create our scheme for this reference frame. So the first thing we have to do is truncate, because we have this infinite spatial domain. So we need to truncate and create a finite dimensional domain, or a finite computational domain. And because of this condition that u approaches 0 near infinity, what we have is these really flat solutions out near the computational endpoints. So we just take the computational endpoints large enough that we can see those flat solutions. To capture the coupling equations, we actually place 2 nodes on each interface. So we have 2 nodes on 0 and 2 nodes on L. And we also do not assume any uniform spacing. And basically, this is because we don't need to have uniform spacing. When we have these really flat solutions, we don't, near the computational endpoints, we don't need to find mesh. However, where we have these jumps and steeper gradients, that's where we want to concentrate our efforts. So that's where we use a finer mesh. Okay, so our scheme for stability is upwind, forward, backward Euler method. A here is going to contain all of the spatial finite difference coefficients. M is a diagonal matrix where it's 1 everywhere except for the equations that are irrespective of time. So that would be like the coupling equations. And F contains all the nonlinear information. So it's only non-zero inside the suitable habitat. Okay, so we want to validate this scheme. And we go back to that case where we have all that analytical information where the L1 and L2 are moving at constant matching speeds. So we can verify, we can use that analytic information to help verify our numerical solutions. So for example, we know exactly when our solutions should be always decreasing inside the suitable habitat. We know exactly when we should see a local maximum inside our suitable habitat. We know when we should see persistence or extinction. Another thing that we want to do is have grid independence. So we don't want to see large or significant variation in the solution by changing the grid size. So what we do is we numerically compute a reference solution over a very fine grid, and then we compute a numerical solutions over varying grids. So for example, coarse to fine, we calculate the error between each numerical solution and the reference solution. And once that is less than 1%, then we've achieved the desirable grid independence. So now I'm going to move to application. I'm going to look at the application of the constant non-matching speeds. So I'm going to look at a growing domain. So I have L1 moving at C1t, where the speed is C1, L2 moving at L plus C2t, where the speed is C2, and C2 is bigger than C1. So I'm going to look at the effect of the trailing edge, that's L1, and the speed of the trailing edge on persistence extinction outcomes. So just for one moment, I'm going to go back to the case where C1 is equal to C2, is just call it C, moving at that constant matching speed. In that case, we know that for every parameter set, there is a critical threshold speed above which the population will always go extinct. And in this case, that speed is C star equal to 2. And this is also the Fisher speed, which is the speed at which population invades in a homogeneous landscape. That means that there's no structuring of like good and bad. So we're going to let C2 be bigger than this C star speed. And then we're going to take C1 at varying speeds, kind of going around the Fisher speed here. So the first, for this left, we have figure with C1 equal to 1. And we see this invasion front establishing, and it's actually moving at speed C star equal to 2. When C1 is equal to 2, we see for these later times, so the time is the vertical axis. So we see for later times that it kind of looks like this traveling pulse solution is somewhat established as the population hangs on for dear life at the trailing edge. However, before that, we see this large expansion of the population behind the trailing edge. And we call the population that's existing behind the trailing edge the zombie population. And then for C1 greater than the Fisher speed C star, we see this detachment from the trailing edge. The population is basically totally left behind, and it just goes to extinction because of dispersal and mortality. So what we learned is that the population will go to extinction if L1 moves too fast. So even though the habitat is growing, extinction is still may happen if the shift is too fast. So now let's look at how alpha affects these dynamics. So the preference for the trailing edge. So I have three graphs here. The total population is the farthest left one. The ratio of the total population in the suitable habitat over the total population is the middle one. And then we have the range, where range is just the largest interval in which U is greater than some arbitrarily chosen constant, is the last graph here. So let's start with the green curves with the circle markers, where alpha equal to 0.5 is the solid curve, alpha equal to 0.8 is the dash curve. So in all cases, we see increasing behavior here across all these graphs. The interesting point here, though, is that alpha equal to 0.5, so that's actually no preference for either habitat, sustains the larger population. And we can see that it also sustains a larger range. And this connects to each other, because what happens is that zombie population is actually just bigger and it's longer. And so that's why we see that alpha equal to 0.5 sustains a larger population. Now let's move to the orange curves with the cross markers. In this case, we see the opposite effect. Alpha equal to 0.8 sustains a larger population.
2 minutes.
Great, thank you. And we also see this drop in the range. So what happens here is that, remember how we saw that kind of hump that disappeared and then that carrying on for dear life? So once that hump disappears, that range drops when alpha is equal to 0.8. And it's just less, we don't see such a big effect when alpha is equal to 0.8, and plus when alpha equals 0.8, it sustains a larger population because the population is better to holds on better to that trailing edge. In the last case, when we have these curves with no markers, both populations go to extinction. However, we see this effect where the alpha equal to 0.8 is related to that drop, and this is because it holds on better, right? So it's actually explained in a very similar manner. However, with the case 0.5, we have that large detachment and then that kind of gradual decline to extinction. And so that's what we see here. So in summary, we built a finite difference scheme applicable to deforming landscapes with coupling across the interface. We validated our model numerically, and we applied it to a motivating phenomenon of climate-driven moving habitats. The scheme is efficient, accurate, and easy to implement. The scheme provides transient dynamic insights. For example, we have that expanding zombie populations can indicate a high-risk population. And we're also looking at other investigations. So accelerating speeds of habitat shift are in the same paper that this work that I've presented to you here today is in. We're looking at periodically varying speeds of habitat shift. And that will be submitted in the near future. And we're also looking at the two-dimensional analog, which we're not taking a finite difference approach, but rather a finite element approach. So I'll just acknowledge both my supervisors, Dr. Fithiof Lucher and Dr. Yves Bourgault. The highlighted orange is where you can find the work that I presented today. And then the other references are also very good references if you're looking into moving habitat models. So thank you very much.